I'm delighted to be here, and I can't see a darn thing. So hold on for a second while I turn on the robot here and get the laptop running. Anyway, I wanted to tell you how proud I am and pleased I am to be here to talk with you about the story of the universe. And I will tell you some of the story of the universe, not the whole thing. So just a sec here, if we get the machines to play well. Do we see something? Yes, it works, miraculously. So maybe if I move around a little bit, I'll be able to see you better. Anyway, what we have to tell you about is the history of the universe from the beginning to the end. And I want to confess that there's already a mistake on the first chart, because there isn't a beginning that we can see, and there isn't an end that we know about. So, but I'll tell you something about what's in between. So, I think our enterprise as astronomers has a pretty important cultural context, because I think about what Jefferson wrote in our Declaration of Independence. And he wrote something that means something to me. He was, as you know, the person who sent off the first federal scientific expedition to explore the western part of this country. And that project, as you also know, was over budget and over scheduled by a lot. But it turned out well in the end. So Jefferson wrote, how is it, well, he wrote, I write, how is it that, as he said, the laws of nature and of nature's God can lead to this? We hold these truths to be self-evident, that all men are created equal, that they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. Well, if you're a scientist, you say, well, I can work on some of this. And I'll tell you the part about the physical universe, and then we have to say, okay, that's beyond physics. We have to talk about biology, history, psychology, sociology, and many other things to get to the rest of this. But it's all very important, and so I'll tell you what we can tell you about our own history, the physical part of the history. So we do this as astronomers by taking pictures of the sky and trying to understand what they mean. So this one, can you see that? Okay, it's not too bright. So what we see here is a picture that's called the Hubble Ultra Deep Field. So we pointed the Hubble Space Telescope in one direction where there was nothing to look at that we knew about for a couple of weeks. And what we saw actually were thousands and thousands of galaxies, and these are them. These little fuzzy balls are ovals. They're different colors because they're at different distances. They have different ages. And so these are representatives of the history of the universe. We live in a galaxy. It's called the Milky Way Galaxy. And the Milky Way has about 100 billion stars orbiting around a common center held together by gravity. But we'd like to say, well, how did that happen? How did we get here from whatever was there before? So this picture that I'm showing you here is part of that story. If we could understand what it's telling us, we would be able to see that we're looking back in time to see as galaxies were when they were younger. So this is part of our challenge. Next part I want to show you is this another part of our history. This is a star that exploded in 1054 AD. It was observed by Chinese astronomers. Nobody else seems to have written it down, but they kept records. So we know from 1054 that this was a star. And it was so bright you could see it in the daytime. Now what we see is this enormous cloud of expanding debris. And what we look inside, we see, well, there are X-rays coming out. And we can do the chemical analysis on what's in there, and there are all the elements of life are in this star that blew up. So that's a really important part of our story. The elements of life are liberated by stars going back out into the gaseous material between the stars by these explosions. Part of our story. We have also taken pictures of stars being born. This is a picture taken by the Hubble Space Telescope, and what we see in the middle, I don't know if I can get my pointer to point. See if it'll point. See this little thing up here? It's a little whirligig, which is really a star in the process of being born, and is sending out jets of material from the North Pole and the South Pole because it's spinning, and material is trying to fall in. So we know that this is a place where a star is being born. Many, many are visible to us. If you look with your own eyes at the at the sword in Orion, it's a little cloud. It's not just a star. With binoculars, you can see that it's a fuzzball. and inside that are some brand new stars. So we know where to look for new stars. We can see eventually how are stars like the sun being born today. So that's part of our history, and part of it's just beautiful pictures. So back in 1985, NASA was trying to explain to the Congress why we needed to build 4 great observatories. Not just 1, but 4. So you all know about the Hubble Space Telescope because it's very famous and it's still operating. But we actually had in mind 3 other ones. There's something called the Chandra Observatory, which is an X-ray observatory. There's a Spitzer Space Telescope, which is also still operating. It measures infrared light. And we had the Compton Gamma Ray Observatory, which we've aimed into the Pacific Ocean because it might have hit something. We accomplished the objectives that we had in mind in 1985 to answer these kinds of questions. How did the universe begin? And like I said, it didn't really, but we'd like to know more about it. We know about the early universe and how it's been expanding and cooling. Would we find new laws of nature about the early universe? And in fact, we have. We have found out about something called cosmic inflation that happened in the first sub-microseconds. We have found out about cosmic dark energy, which astronomers can recognize even though we can't see it. We call it dark. We have found something called dark energy, which we also cannot see, but we can deduce that it's there. So we have lots of new mysteries to explain. We have learned something about how the galaxies form. In 1985, before the Hubble Space Telescope was launched, we had many wonderful theories, but they were wrong. So we got a picture, and we knew immediately that those theories were wrong. So there's a great power of observing. So on the right side, we have more local questions. How are the stars born? So when I was a graduate student, when I was a college student, we knew in general that the picture that I showed you should be true. But to tell you the truth, we cannot get it to work out right in the computer, so we don't honestly know yet. We didn't know in those days what happens when a star dies. We know many of them will be like the sun will be, where it just expands and then shrinks down to a small object the size of the Earth. We call that a white dwarf. But other stars that are bigger will explode. So how does that happen? We still cannot make that work out in the computer, so we don't really know. Did black holes exist? Well, a star could possibly collapse into a black hole when it's old. We didn't know that in those days. Now we know that there's a black hole in the middle of almost every galaxy. And our own Milky Way Galaxy where we live has one too. And in fact, just recently this week it was announced we know that it erupted in about 2 million years ago and sent out a huge flash of energy. Now, how can a black hole erupt? Well, things fall in and they get hot, and that's what we see. So how are the planets formed? How are the stars formed? Well, we didn't know then. We still are not sure, but we have some better ideas. And I'll show you more about how we're going to learn about these things. So now perhaps this is a surprise to many of you. When you're looking in the mirror in the morning, you can be a cosmologist as well as a cosmetologist. So the atoms that you're looking at in your face, in your body, did not come from the early universe. They came from stars that blew up, like that beautiful Crab Nebula that I showed you. That's the place where the atoms of life are liberated back out into space. They go out, maybe even out of the galaxy, and they fall back in and they are recycled. So not only is everything recycled locally today, our own atoms have been elsewhere. We have been inside a star already, only we don't remember. So everything's pretty recycled. So now a few words about how we know some of these things. We're not just making this up to have fun over beer. We actually look back in time. Astronomers really do look back in time because light travels fast, but its speed is not infinite. So when you look at something that's far away, you see it as it was. When you listen to a thunder at night, you can say how far away it was because you can tell that the sound takes a while to get here from there. Same thing with light, only it's just faster. So if you look at something far enough away, you can see really quite far back in time. You see the nearest other star as it was 4 years ago when it sent light to us, the center of our galaxy, about 25,000 years ago. If you could look all the way back to what we call the Big Bang, it would be, when I drew this chart many years ago, it was 15 billion years, and actually 13.8. So we can look back in time. Our penalty is that we get to look at fuzzy things. And no matter how big a telescope you build, it's still going to get a fuzzy picture. Nevertheless, it's worth doing. So next question is, okay, I do believe that we're looking back in time. How far are we looking? We have to do some surveying. So we look at the sky and we do what the ancients did. We draw triangles. If you know one side of a triangle, and you know two angles of a triangle, and you believe your geometry according to Euclid, then you know the whole shape of the triangle. So you can survey the universe this way. So the Earth moves around the sun, so we actually have some measured distances this way. It works pretty well. In fact, the ancient Greeks were able to do this. They measured the size of the Earth this way. They measured the distance to the moon this way. They attempted to measure the distance to the sun, and they couldn't get it because it was too far. But the basic method was known to the ancients. A very similar method is if you look at two things and you say, I know those two candles are identical, but one is fainter than the other. You say it's just because it's farther away. This is a kind of the geometry problem. So this is the basic tool of astronomy for surveying distances. Pretty simple, but pretty hard. So, okay, now we can measure distances, so now you know how far back in time you are looking, because you know the speed of light also. Now we say, well, how are things moving? That's the next step. Let's see things move. Well, the planets move, the moon moves, the sun moves, it appears to move. So, but other things that are far away, they don't move enough to notice. So what else are we going to do? It turns out that if an object is coming toward us or going away from us, it changes the wavelength of light that we're going to receive, just as a moving train whistle would do, or a truck as it goes by, the pitch will change. So we can use this effect to determine the speed of something coming toward us or going away from us. So you spread out the sunlight with a prism and you get these things that they're marks across the spectrum of the sun. We call them spectrum lines because that's what they look like. So each different atom or molecule or ion in the surface of the sun produces its own wavelength, which we can measure and recognize this way. So you say, okay, now I know about the chemistry of the sun, but now let's look at another star. And well, you very often find that we see the same pattern, but the wavelengths are all different in a systematic proportion. So we say that's because the object is coming toward us or going away from us. So now we can measure the speed of motion of different things. No matter how far away they are, if they're bright enough, we can measure. So this led to a totally astonishing discovery in 1929. Here it is. This is a plot that Edwin Hubble published in 1929. It became instant news on the front page of the New York Times. And what he saw was each of these dots here is a galaxy. In the horizontal direction, he's plotted the distance. On the vertical direction, the speed. So what he found is this amazing trend that the speed is proportional to the distance. Proportionality. So what do you do when you do that? Well, you say, let's figure out how long it takes for everything to get there. So you divide this distance by the speed, you get the age of the universe in 1929. So this is a big surprise. It was front page news. It was good news in a way. We discovered something about the expanding universe at the same time that we discovered the worldwide economy could collapse all at once. So people have been tracking this for ever since. This was a huge, huge discovery. And by the way, Hubble was wrong about the age. It was a big puzzle for us. He said it was about 2 billion years and it's really 15, so that was a problem. In fact, in a little while it was figured out that the Earth was older than the universe. So that could not be. It made a big trouble. It took a long time to find the mistake that he made. Now, some pictures of some famous people that you will recognize maybe some of. In the middle, Albert Einstein. In 1905, he said, guess what? Space and time are not absolute. They are mixed together. The laws of nature tell us this, and you cannot tell whether you're moving or not. So he gave us relativity. A lot of people said that's nuts, but you know it fits the data. So it does, and he was right. We still have not proven him wrong about that. In 1916, he said, not only that, but space is curved by the action of gravity. So it's not that there's a gravitational force, it is we are falling through a curved space. So this was a pretty weird story, but he's still right. We have not found that one to be incorrect either. And so 1916, he says, I know this, and predicted a few things that we saw. So we pretty soon knew that he was correct about that, as near as could be. So 1922, this young man over here on the left, Alexander Friedmann, said, I can take Einstein's equations and I can predict the motion of the universe. And he got the right answer. He said the universe must be expanding. Then 3 years after that he died because Leningrad was a terrible place to live in 1922. So he did not get to find out that he was correct. 1927, this young man, Georges Lemaitre, who is a Belgian scholar, a priest, a Jesuit priest, and also an MIT PhD in physics, worked out the same equations again, and he got the same answer, and he got it published. So Mr. Einstein said, well, your mathematics is correct, your physics is abominable. Basically, Einstein was a very intuitive guy. He knew the universe could not be expanding. God would not do that. That's his opinion. So it was only 2 years after that that we saw Hubble's plot that I just showed you, and Einstein had recognized what he now called the greatest blunder of his career. So I told you I would explain the greatest blunder of Einstein's career, and that was it. Curiously enough, maybe he was right after all. I'll show you later. Other people on this chart, George Gamow was a Ukrainian physicist. In 1948, he was at the George Washington University in DC and calculating things about the early universe. This is after the war is over, you can start to apply your nuclear physics to the cosmos. And he recruited these two young men to his topic. They're not so young in this picture. This is what they looked like when they came to the launch of the Cosmic Background Explorer satellite that I'll show you later. Anyway, these men said, we know how to calculate something about that early universe. The universe should be full of hydrogen and helium in a constant proportion, and they got the right answer. They also calculated the universe should be full of heat radiation because the early universe was hot. So where did that radiation go? It's still in the universe, and they got the temperature. They got 5 degrees Kelvin, 5 degrees above absolute zero, and that's pretty darn close because they had slide rules, and we have digital calculators. We now know the number is 2.7, so they were darn close. The other two gentlemen here are current day physicists, and they're still in the business of telling us what we're going to find before we find it. So now, a surprise perhaps for you. Hubble's law tells us there is no center and no edge of the universe. Now, when people say the Big Bang Theory, almost everyone that I know will picture a firecracker going off over there in the corner at a particular time and place. But it's not actually what astronomers see. What we see is an infinitely expanding universe that's already infinite when it's young. So this is a little hard for people to accept, although it's extremely simple. So here's an example of what 3 astronomers might see. Here's an astronomer on the left calculating the motions of these other astronomers. Astronomer on the left says, okay, I see my universe is 1 hour old and all the others are leaving. Astronomer in the middle, she says, well, I can get the same calculation. My universe is also 1 hour old, and all the others are leaving where I live. Astronomer on the right can calculate the same thing and gets the same age of the universe. So they all calculate the same age of the universe. They all think they're in the middle. Conclusion is, there's no middle. So that one small confession here, it doesn't mean there's not a middle, but it means we cannot find it. It is, and we've been hunting. We've been looking for a long time. There is no place that looks like a special spot that is the middle. There is also no place that looks like the edge either. So I'm sorry, everybody is sure there must be a place where this Big Bang occurs. No, I'm sorry, it's everywhere. He went that way. So this is one of those great conceptual puzzles. It's actually extremely simple, but we don't like it. It means also if somebody draws you a picture of the explosion, they are by definition incorrect. So I'm not going to draw you a picture. This is the best I can do. So the explosion is not an explosion. It's the entire infinite universe expanding. It did not happen over there. It happened everywhere. And it does not actually have a beginning because there's no first moment. The universe did not spring into existence. It has always been here. It's only, the clocks have only been ticking 13.8 billion years. So a lot of things you hear in popular press about the early universe are incorrect. And it's just hard to do it. I even lied when I got you to come by telling you about the Big Bang and the beginning of the universe. So anyway, pardon me for that. Now I wanted to tell you a little bit about the next step. You look around you and say, well, my universe is not expanding, our solar system is not expanding. Why do you guys think it's expanding? And how did we get here from that early universe? If the early universe was expanding, we're not. What happened? So our story is gravity is capable of reaching across immense distances of space and pulling back on material. So here's a body, there's a gravitational force between them. Start them off going apart, they'll gradually slow down, and if they're not going too fast, they'll fall back in and hit each other. So that's what we think happens. The early universe has places that are able to stop expanding. So we live in one. Our galaxy stopped expanding, it made stars and planets. So this is one of those wonderful paradoxes about the early universe, and it seems to be true. So this gravitational force did it. After you've got the stars and the planets going, then of course you have this situation where you could have life. So now I can summarize for you the early history of the universe in one single chart. And here it is coming up. Okay, so the picture in the upper left is a map of the sky as observed with microwaves. So it's actually the universe as it was when it was young. Then we have a story. Oh, you're giggling because of the horrendous space kablooey? That's actually the name of the Big Bang as suggested by Calvin in the Calvin and Hobbes comic strip. And my boss actually got me the original drawing of this cartoon because it's a wonderful thing. Anyway, it is named that because Sky and Telescope magazine held a contest to rename the Big Bang because they said it's a bad name. And this was Calvin's submission, but we didn't get to keep it. So it's still called the Big Bang. Its name is stuck even though it's a rotten name. So anyway, we have this story that the galaxies form by material falling together, as the streams run down the hillside, they come together to make a big river. So too we think the galaxies are formed by big things coming together. So here, for instance, we've got a picture of the Andromeda Nebula. If you've got a Macintosh, maybe you even have this picture as your screensaver sometimes. And what you see here is the big nebula, and there's a little galaxy there that's falling in. It's going to get swallowed up by the big one. So the story here is we've got this expanding universe, starts off in some curious way, gives everything that's going to turn into anything is there in the early universe. And when the universe is about 3 minutes old, all the nuclear reactions are over, and we have hydrogen and helium. That's it. That's how we know how the universe starts. We calculate this because the temperatures were so extreme, and we actually can measure these kinds of conditions here on the Earth. So we're not making this up. We actually have measurements that say this is right. We calculate then at a certain time the universe cooled off to when it became transparent. And the heat radiation of the early universe could come in a straight line straight to your eye. So after that we can then make a map, and that's what this picture in the upper left corner is. The heat radiation of the early universe as it comes to our instruments. Then we've got the rest of the story. The first stars form, the galaxies begin to form, and then at the last line of this chart I tell you a surprise. The universe is now no longer slowing down, but it is accelerating. And this is pretty weird. I'll come back to it later. So, okay, so this is a pretty wild story, but possibly true. We won't know it's true for a long time, maybe never. But anyway, so how did the Earth form? This is not my specialty, but I love the story, so I just want to show you a picture of how it might be that the solar system formed, because I'd like to know how we got here from the early universe. So we have a definite measurement of the age of the solar system because we can pick up little tiny dust grains and do isotope analysis and see about the uranium and thorium that were in there and were radioactive. So we can date the solar system. And then we say, okay, well, how did that work? And we got a lot of stories, probably incorrect. We do have some pretty interesting evidence that the moon was formed by a collision between an object about the size of Mars and the Earth, because we can simulate that in the computer and make it sort of look like what we have. And then I have a wonderful surprise to show you that the early solar system was not stable. We see the solar system orbiting around, and the The planets just keep on going around in their orbits all the time, and it looks like it'll keep on going forever, but it might not. And in the early solar system, it wasn't stable, I think. I'll show you the idea. Anyway, for hundreds of millions of years, we had rocks crashing into the Earth, comets, asteroids. Some of them were good for us because they probably brought water and carbon so we could be here and be alive, but they also made a big mess. Every time the big one would fall, it might have vaporized all life. So that all happened, and then it all stopped about 3.8 billion years ago, and then presto, within almost immediately, we have fossils that look like they were alive right at the end of the bombardment. So this is point number one, is how common is life in the universe? Well, it looks like it started right away here as soon as it could. That's one observation. Not conclusive, but one observation. So here is the simulated early solar system. What we have here are the orbits of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. And the little green things are the leftover rocks, the asteroids, the comets, the dwarf planets, whatever is out there in the outer part of the solar system that never turned into a planet. So the simulated solar system runs along for almost 1 billion years, and then suddenly the planets go haywire, and they shift their orbits around, and a huge bombardment occurs where all the little green rocks are flying in and hitting the planets. Look at that. This is just computer simulation. This is just gravity operating between these objects, but it's unstable. So now we know we cannot prove that the solar system is going to keep on running like it does in the future either. Maybe it's kind of lucky that we're still here. Anyway, we know we're here, so it worked out. So I promised to tell you about the future, even all the way to the end of the universe. So a little bit. So we've been doing astronomy with telescopes for 404 years now. We celebrate that quite nicely. There are a few trends you can see. We are using up all the coal and oil we can dig up as fast as we can go. And we like using it, but we don't think we're going to like the result. So it is going to get warmer. It is getting warmer. If I knew exactly how much, you wouldn't believe me anyway. Cassandra and Tiresias were people who committed crimes in the ancient mythology, and their punishment was that they did know the future and nobody would believe them. So I'm not going to tell you that I know the future. So, but a few things we are pretty sure of as astronomers: in about 1 billion years, the sun is going to get so bright that we can't live here anyway, no matter what we do, because the sun, this is what stars do when they get old. They use up their nuclear fuel, they restructure themselves, they get bigger and brighter. In about 5 billion years, the sun will become as large as the orbit of the Earth. We will be orbiting within the surface of the sun, and we better do something, if anybody's here by then. At around the same time, a remarkable thing is going to happen, and I'll show you a movie later, that the beautiful Andromeda Nebula that I showed you a picture of is headed straight for us, and we will have a collision. So it will be a very interesting time to be an astronomer. And then in 7.6 billion years, it says the sun is going to go out. That means it's going to shrink down to become a white dwarf because its nuclear fuel will be used up. So that's the beginning of the cooling off. What we think is all the stars are going to go out after a while. As the universe continues to expand and accelerate, all the distant galaxies will go away. So we will think, if we're still here, that we are the only ones left. Then if we believe what Stephen Hawking tells us, all the material that's in the stars will eventually fall into black holes. And into the incredible trillions of years, the black holes themselves will evaporate, and there will be nothing left but an extremely cold, empty, uniform universe. So that's what that story is. Do you believe it? I don't know. We don't know why it's doing what it's doing, so there's no reason why we should know what it's going to do, right? So I'm not promising. But at any rate, it's not soon. Now I want to show you a little bit about the work that led to the Nobel Prize, so you have some idea of what we did and why it was important. So in 1974, I got out of graduate school. My thesis project had failed, and I decided to do something else, so I got a job working for NASA in New York. And then 6 months later, NASA said they wanted proposals for new missions, new satellite missions. So this is 5 years after the Apollo landing. What is NASA going to do besides manned spaceflight? So they said, send in proposals. Well, my boss said, okay, I agree. Your thesis project should have been done in outer space. We will we'll get a team, we'll write a proposal. We sketch something like this picture. Oh, sorry, next picture. We sketched this picture on a napkin, and we called up our friends, and we wrote a proposal, and in a few months we had sent it in, and we said, we have a good idea. 2 years later, they said, yeah, it's a good idea. We'll appoint you to study this some more, and we'll give you access to NASA engineers, and we'll think about how this really could be done. A couple of years after that, they said, well, we're not going to use that kind of rocket anymore. We're going to use the space shuttle. Have to redesign. So then the Challenger exploded in 1986. We're going to have to redesign again. So we went back to the original story, and this is what we flew 15 years after the napkin sketch. So what did it do? Well, it had 3 experiments on board. One was measure the brightness of that cosmic radiation and compare it with the prediction. The expanding universe theory says there's something called a black body function, which we study in basic physics. And it's this smooth curve here that you see in the picture. And there's only one number that you have to put in to get that curve. It's the temperature. So you know what? All the measurements are right on the curve. I showed this graph to the American Astronomical Society, and they gave us a standing ovation. I'm told it's one of the first that's ever happened. So I just thought, why are they cheering? Didn't everybody know that was the right answer? But of course, I was looking in the back of the book because I knew in advance what this was the answer. But in truth, we had many bad measurements and many really bad theories to explain the bad measurements that preceded this, and so it was a huge relief for scientists. And it meant that the expanding universe theory, I'm trying not to call it the Big Bang, was probably correct. And nothing else has ever matched this curve the way this one does, so it probably is correct. So the people that believed in the steady state theory, you probably heard of that, they've died. They never gave up, but they died. Our next discovery, a couple of years later, was this set of maps. Each of these ovals is a map of the entire sky. And of course, it's like taking the Earth and trying to put it on a sheet of paper. Each of those ovals is like the map of the Earth, only it's the sky. That what we've done is to make a map of how bright is this cosmic heat in each different direction. In the top curve, we've got that it's a little brighter in this direction and a little fainter in this direction by about a part in 1,000. That's because Earth is moving relative to the rest of the universe. We say, well, we knew it was moving, take that away. We get this picture in the middle, and what we see now is a red band across the middle, and that's the galaxy that we live in, that's the Milky Way. So we say, we knew we lived in the Milky Way, take that away. And so we end up with this map at the bottom, and it's made of these blobs. And these blobs are extremely, extremely, extremely faint. They're a part in 100,000, different from the average, and the average was only 3 degrees. So we showed this to the public, we put it out, and Stephen Hawking said, that's the most important scientific discovery of the century, if not of all time. So it took me a while to appreciate that. So now, why would he say that was so important? Well, now we can interpret it a little better. We calculate that the reason that we are here is because those blobs are there. I told you this story about how gravity has to reach across space to stop the expansion. These are the seeds that will allow that to happen. These darker regions on this one, the sort of aqua-colored ones, those are the more dense regions, and those are the ones that have enough gravity to stop expanding and turn around and collapse back down to make something. So, darn if that didn't turn out. So maybe he was right. We're here because of that. So we were pretty worried as a scientific team that we might have made a mistake. And so everybody else was worried too. But a few years later, our team members, some of our team members, built a new satellite, and they got this map. It's called the Wilkinson Microwave Anisotropy Probe. was also built at Goddard Space Flight Center with Princeton University, and it agrees exactly with the first map. So we got it right the first time, and now we have a lot more detail. So after this map was published, we can actually calculate a lot more, and we can tell you that it fits the expanding universe picture perfectly, but only if we got some really weird stuff. We need dark matter and dark energy. So like I said earlier, astronomers say that it's there. Nobody else can see it. So it's a little embarrassing, but it's also a wonderful scientific challenge. So because we got it right the first time, the Nobel Committee actually called us up in 2006. I think it's October 3rd of 2006. The phone rang at 5:45 in the morning, and they wanted to know if I was the right John Mather, because they had something to tell me. So it wasn't a prank, and so they awarded us the Nobel Prize for the discovery of the black body form, and that's that smooth curve with the little boxes on it, and that matches the theory. And the anisotropy. Anisotropy is a Greek word, and it means not. That's an. Iso, the same. It's not the same. Tropy, direction. So it's not the same in every direction. The universe has bumps on it. So that's what we found. Well, thank you. I got to show this chart a lot. And finally I got to go meet the King of Sweden. He gave me my diploma, which a little while later came with a big check. By the way, we put the check into a foundation to support science and the arts. My wife's a ballet teacher, so we send some to dancers, and we send some to bright young physics students, especially the ones that come to be summer students at NASA Goddard. So if any of you are or would like to be summer interns at Goddard, you should pay attention in January or so and look us up and apply. Anyway, I've done this a lot. It's lovely to be traveling and telling the story. So, but coming back to the astronomy, I told you we had some mysteries, and everyone was sure for like most of a century that because gravitation pulls things together, that the universe will surely be slowing down. Just like I said. So, however, in 1998, these three men here were part of teams that said, no, it's not. It's accelerating. The way they did it was using the Hubble Space Telescope. They took pictures, they measured the brightness of standard candles, and they said, these things are too faint. They're 20% fainter than they should be. Therefore, they're 10% farther away than you said. Therefore, the universe has not been following the curve of expansion versus time. So sure enough, it stood the test. They were granted the Nobel Prize in 2011 for discovering this one. So we've got lots of prizes for cosmology, and who'd have thought it? The first one, by the way, was in 1976, I think, when the people who discovered the cosmic microwave background radiation got their prize for the discovery. So now I'm going to wrap up by talking about the new telescope that we're building, called the James Webb Space Telescope. It's, as mentioned earlier, the project that we're building to succeed the Hubble Space Telescope. So what do we want to do? We want to see infrared light that is different from what you can see with your eyes. So why is that interesting? Well, a couple of things. One is that it comes from the distant universe, because the expanding universe stretches the light into the infrared. One is that you can't see it from the ground, so you need a telescope in space. And one is that things just look different when you use infrared. So you're going to learn a lot of different science if you can see things with an infrared telescope. So we're building one, and here it is. This is not anything like any telescope you have ever seen before. This is not a tube. You do not put your eye down at the end of it. This is launched into space. Will be launched in 2018, 5 years roughly from today. And it is huge. I will show you how huge. But anyway, this mirror is 21 feet across, and it's truly gigantic. It's bigger than the rocket, so it's a folding telescope. This is an international project. It's being led by NASA Goddard Space Flight Center, where I work. But we're working with the European and Canadian space agencies, and we have a major industrial firm called Northrop Grumman near LA Airport that is building the most of this work. We have instruments, cameras and spectrometers coming from around the world. from Arizona, from Europe, from Canada, and so it's coming together. So the telescope is huge, it is cold. We have to make it cold so it doesn't shine and emit its own infrared. It is going to be carried into space on a European rocket called the Ariane 5, so we'll be dragging the boat, taking it by boat down to French Guiana, where they have their launch site. And then we will run it for at least 5 years, we're hoping for 10 or more, to ideally change everything that we know about astronomy. Here's what the model looks like. We had a full-scale model built. This is sort of advertising for the company, because they have other government customers that are interested in large telescopes. And you can imagine what you need a big telescope in space to do. Anyway, this is huge. There's a little person down here in the corner here. So just to give it a little scale, this shield, here's this big umbrella, is about as big as a tennis court. So imagine Roger Federer running back and forth on half of this. And then you have some sense of how big it is. And then you say, and you're going to get that into a rocket, and you're going to fly it. I'll show you how. So here's a little bit more about how it works. Side view, you see this, the big umbrella has got 5 layers. You're able to look through between the edges. There's a box on this side which faces the sun and the earth, has the solar power, the rocket jets, all those kinds of things. And the telescope is always in the dark on the cold side. So if it was a real picture, you wouldn't be able to see the telescope at all. But of course, the artist can draw it how he likes. Here is a drawing that shows how it folds up inside the top of the rocket. A long time ago, we said we were going to build a bigger telescope, and it was going to be 8 meters across, almost 30 feet. And you know, it wouldn't have fit. It's too snug. It's a snug fit the way that it is. Now I'm going to show you how the Origami telescope unfolds. Here's the movie of the unfolding. If you saw the 7 minutes of terror video about the Mars landing, this is our couple of weeks of terror video. This will actually go much more slowly than it's showing here. But first we unfold the solar panels. We need about 2 kilowatts of solar electric power. We unfold the telemetry dish, the little parabolic antenna, to send the signals back to Earth. Now we're unfolding the big umbrella. Now we're going to separate the telescope from the warm box so it can cool off. Telescope needs to be cold. Now unrolling the protective covers. Some more covers. If you're not a little scared by this, you're not paying attention. It means that we have to rehearse and rehearse and rehearse this thing because we have no chance to fix it. We are going to be putting it very far away from Earth, and I'll show you where. And so we all think about things that can go wrong. We have big lists of things that can go wrong. We have people have done this kinds of thing before, and we get them together to complain. And they tell us that we're doing it wrong. And we say, okay, we're doing it wrong, we'll fix it. So that's how it is that you have a chance to build such an incredibly challenging engineering project, and it could actually work and do the right thing. So there it is, outer space. And it's almost ready at this point, except it's still warm. It takes about 2 months for it to cool down to the right temperature. And then when it's cold, then we have to focus it. Here's where we're going to put it. We put it 1 million miles away from Earth. This drawing is not to scale. There's the sun, the Earth. Here is something called the Lagrange point, L2. So it's 1 million miles farther out from the sun than we are, and we put the telescope in orbit around that spot. Is that working? Yeah, I can barely see that. Anyway, this spot was discovered before this country declared independence from good old Mother Britain. And so people could do a lot with a pencil in 1772, you know. It's a good place to put the telescope. So how are we going to do this? Well, I'll show you a little bit about the engineering. Here's a picture of 6 of the big hexagons. The big mirror is made out of 18 of them, and here are 6 of them in the test chamber down at Marshall Space Flight Center in Huntsville, Alabama. And so this is where we test them to see if they're the right shape when they are cold. because they're going to be operating at 45 Kelvin, 45 degrees above absolute zero, and they will shrink, and they will distort a little bit. So we have to measure and make sure. We have to practice focusing, because this thing is not going to be in focus when we launch, so we built a small model so we can practice. So each of these mirrors here has 7 motors on it to adjust the position and the rotation. And so we have well over 100 things we have to adjust to get this thing to be in focus. So we got to practice. So we did, and now we think we can do this. By the way, if you had just believed in calculations and computers, you would not have gotten it right. Sometimes you do have to build it. Here is a drawing of our most complicated instrument. This one has just been delivered to Goddard Space Flight Center from Europe. The purpose of this one is to make a rainbow out of every galaxy that we look at. So a rainbow, to spread the light out into a spectrum so you can tell how the object is moving and what's in it. So this amazing thing, it's about 6 feet long from one end to the other, and is made out of silicon carbide, which is a remarkable material. You would say, don't we make grinding stones out of that stuff? And it's also an aerospace material, so you would have never known. Anyway, this has an ability to measure 100 different galaxies at once, because we have shutters we can open up in an indesired pattern. Here they are opening up in this particular pattern. There's no galaxy that's shaped like the lion here, but this is so we can choose which galaxies we want to look at. And here I have the device that makes it possible. We have these little shutters that can be opened and closed by command from the ground. So we sit here on the ground, type away, and send a command to open this shutter and close that one. Let this galaxy in and reject that one. We have a giant clean room over at Goddard Space Flight Center. This is how it looked a couple of years ago when it was empty. So this is a clean room where you keep all the dust off of things. If you want to watch us put the telescope together, you go to this website here, James Webb Space Telescope, JWST, and you can actually watch our people running around in their white bunny suits, putting it together, taking it apart, doing their job. What are we going to do to prove it's okay, that we're not in the same kind of trouble that the Hubble Space Telescope was in? We will take it to Johnson Space Flight Center, that's in Houston, and we will put it in the giant tank. This is the same tank that the Apollo astronauts used when they were rehearsing getting out onto the surface of the moon. So it's old. It's on the historic register. You have to fill out paperwork when you're going to say you're going to change it. But we have changed it. We've put in cooling fins all through the inside, cooling shrouds, so that the inside will go down to a temperature of only 10 degrees above absolute zero. And so that's enough so that the telescope will be cold. We'll be able to tell if it focuses the way it's supposed to. So this is a very difficult experiment, but this is what it takes to make sure that that amazing thing will work. So now I want to wrap up with a few bits about the science we hope to do. I told you we don't know how the galaxies are formed, but we have computers. And so this is a computer simulation, just like you would simulate the weather, of how the material in the early universe pulls itself together under the action of gravity. And so you could do this too, only you need a bigger computer than you have. This takes one of the biggest ones in the world to do this. Anyway, the gravity does indeed pull the stuff together to make a compact galaxy there in the middle. You can see it gradually beginning to spin up. We think that's how our Milky Way galaxy grew. So done in the University of Illinois, actually, Champaign-Urbana. So do I know this is true? No, I don't. In fact, I asked the people who do these calculations, are you ever going to tell us how it is before we go take a picture? And they say, no, probably not. And it's too tricky. But at any rate, you can imagine that you might get close. So we also can simulate the event I told you of, where the beautiful Andromeda Nebula is headed straight for us. And so we have a computer simulation of that. We'll have to wait a couple billion years to find out if this one's correct. But here you have these two beautiful spiral galaxies. They come toward each other, they rip each other apart. The stars actually do not hit each other. They pass right by, because stars are very tiny compared with the space between the stars. So they rip each other apart. They will gradually fall back together. And if I let the simulation run for a while, you see that they merge together. And now you have to say, well, what happens to the sun? What happens to the solar system? Well, you can't tell. Certainly not yet. We have choice of two possible fates. Either we could get expelled and be flung completely out, or we could get drawn into the inside. Either way, it will be exciting. Very amazing possible future for us. So what else might we see? We are going to do something that Einstein told us that must exist, but we would never find. He said gravity operates by bending light as well as space. So sure enough, we have places where this happens. See this pink arc up here? Is it showing up there? Yes. Sort of. Anyway, that pink arc in the upper right corner is a place where the gravity of all these beautiful yellow galaxies is focusing the light of a more distant galaxy. So this pink arc is actually a far fainter, much more distant object that's been magnified for us, and so we can see the details much, much farther away. So we've got a couple of hundred of these in the catalog now, of places where nature gave us an extra lens for the telescope. See farther. We have places to look. Well, you probably have seen this beautiful picture before. This is called the Eagle Nebula. It's a place where stars have just been born, and you can see them burning brightly and shining on the clouds of dust. And you can see that there are places you cannot see because the dust is too thick. It's just blocking all the starlight from behind. So we'd say, well, we'd like to see inside to see how the stars are being born. What if you use infrared light? So we did that from the ground. Here's the same place as seen from the ground. And you see a completely and totally different picture. You see objects like this star over here that you could not see at all before. You see inside these clouds, you can see the new stuff. So this is one of our main objectives of the telescope, is to study how that works. We will study how the planets work. We have already, this picture in the bottom right is a picture taken with the Hubble Space Telescope, and it is a picture that shows a planet orbiting another star. This is a star called Fomalhaut. It's a bright one in the southern sky. And they took pictures. There's 3 pictures now. This one only shows 2. You can actually see the little dot here has moved over a little bit in the course of 2 years. And now we even know the orbit of this planet around that star from watching it for a while. And we knew it was going to be there because this ring of dust orbiting around that star in the middle is like the rings of Saturn, and they are there because there's a satellite that does something. So we knew it would be there. This is the first time since the discovery of Neptune that we were able to predict the location of a planet and then take its picture. But we have another wonderful technique available called transit technique. If you wait long enough, a planet might go in front of its star and block some of the starlight, like in this little movie here. And so if the planet's a big one and the star is small, it's a big effect. You can see it. If your planet is bright, then when it goes behind the star will block some of the light of the planet. And you'll say, aha, the planet just went behind the star. In both cases, you can now begin to learn about what is that planet like. How big is it? How hot is it? And if you're really lucky, some of the starlight goes through the planetary atmosphere on its way to your telescope. So you can begin to tell whether that planet has clouds, whether it has water vapor or ammonia or sodium. All these are things that we've already been able to hunt for. So with this method, we have a hope of finding out if the planets we find are wet. So with the Webb telescope, we should be able to find planets that are about the right temperature and the right distance from their star and the right size to be like Earth, and to see if they have an ocean. So within the next decade, I think we might be able to answer that question. Now, it's a much harder question to say, is that planet alive? What we would have to find to know that from a distance, how about oxygen? Here on Earth we have oxygen because we have plants and algae. And if they weren't there, we wouldn't have oxygen. That's what we think. So if you were able to find oxygen by this method on a planet around another star, you would say, aha, there is life elsewhere. You might not be able to prove it, and you might not be able to talk to them, but you'd have a story you could tell. So I'm going to wrap up here and say if you want to read more, there's more to read. There is a little book called The Very First Light, which you can get from Amazon in the second edition. One time it was 95 cents. I think the price has gone back up. But at any rate, we have also some websites, the James Webb Space Telescope, JWST. This one is for cosmology. The NobelPrize.org website is brilliant in explaining for the general public what our science has meant. And so I invite you to pursue these if you have an interest. So I'll be very happy to have your questions, and thank you so much for coming to hear the story of the universe.